Hello and welcome to SYBERA. Today I would like to introduce you to a special topic, clock synchronous profit drive on a PC basis. Is that even possible? For a long time, profit drive and clock synchronization were reserved exclusively for microcontroller-based PLC systems, such as a Siemens S7. On a PC basis, however, this seems to be a contradiction in terms. Not so for SYBERA. With a standard PC and a PTP-capable Ethernet chip, such as the Intel i210, it should also be possible to implement clock synchronous profit drive. This chip has a highly accurate PTP timer, which provides the basis for the IRT protocol, and that is exactly what we are going to test now. I have a small standard PC here with an Intel i210 Ethernet chip, which we will now use as a PROFINET controller. For our demonstration, we are using 3 drives from SYBERA. The IRT-capable PROFINET stack from SYBERA implements the protocol and control of the profit drive drives. First, we create a configuration. To do this, we use the PNIO Verify software from SYBERA. With this software, we can configure everything for clock synchronous operation. Assigning the station name and IP address, selecting slot and subslot elements, timing settings, topology structure, and isochronous mode settings for the drives. I have now started PNIO Verify. I previously copied the GSTML file for the drives to the PNIO Verify directory. Now I can scan the bus for drives. I select the appropriate type for each drive. In the next step, I select the modules for the drives and delete the unnecessary submodules from the list. Now I'm configuring the connections. I open the dialog box by right-clicking on the module. If no station name or IP address has been assigned yet, I will do so now. Likewise, I select RT class 3, i.e. IRT. The topology must be defined for IRT operation. In our case, the master port is connected to the first port of the first drive. The second port of the first drive is now connected to the first port of the second drive. Once the topology has been defined, the frames and offsets of the modules, i.e., the time offset for clock synchronous operation, must be defined. To do this, it is necessary to determine the delay time of the master port. It is also advisable to increase the frame gap, i.e., the distance between the frames, slightly. Now the offsets can be calculated. Most recently, the settings for clock synchronization must be defined. To do this, I select the corresponding module and open the dialog for setting the submodules with a right click. Now I select the submodule in the list and click on the Set ISO Mode button. Here I can now specify all the necessary settings for clock synchronization. The boundary conditions for clock synchronous operation are specified by the respective application. Now I save the configuration. Now we will create our application. To do this, we will use Microsoft's Visual Studio. The PROFINET stack from SYBERA is integrated into a new project as a C library. In our example, we use this library to create a simple console application. The C code consists of two parts: the Windows code for administrative tasks and visual display, and the real-time code for cyclical data exchange and drive control. Let's first take a closer look at the Windows section. First, a global memory is created for managing the drive variables. This memory can be used both in real-time and in the Windows section. The drive elements are managed in so-called drive set structures. Now the Ethernet mode is adjusted for IRT operation. The path to the previously created configuration file is specified in the parameter structure for the stack structure. Now the PROFINET stack can be activated. After successful execution, the parameters for operating the PROFINETX are returned. These include, among other things, the management list of the specified stations for further programming. Now, the station name and IP address can be assigned optionally for each station, unless this has already been done during configuration. Each individual station can now be activated for PROFINET operation. After that, we are in cyclic operation and can set the PROFIDRIVE parameters for the drives. Now the drives can be activated and functional operation can begin. Some structures are predefined in the real-time part of the application. The application task includes the sign of life, which must be executed for clock synchronous operation. The structures for cyclical data exchange are also specified. For functional operation, the logic function is of interest to us, as it gives us access to the drive's user data. Please note that the user data is transferred in big endian mode. So we determine the pointers to the input and output variables and convert them to the little endian format for our drive set. We now want to start the drives at a specified speed. Synchronous operation is based on Telegram 5 of the PROFIDrive specification and consists of variables such as target speed, error tolerance, and amplification factor. Let's take a closer look at this in practice. Finally, we want to analyze the ramp-up of the drives using the Wireshark software. For this purpose, I use the net analyzer from Hilscher, which can record Ethernet communication without time delay on a nanosecond basis. I will now start the application. Let's observe the drive and the net analyzer software. Once enough frames have been recorded, I stop the recording and convert it to Wireshark format. Now I open this file with Wireshark and see right at the beginning of the recording the DCP and the AP protocol for finding the station name and IP address. After that, I can track the calibration of the delay times, which is done via the PTCP protocol. Now the cyclic PROFINET protocol begins with the connect, write, and control services. To get a better overview, I set a filter so that only the acyclic PROFINET protocol is displayed. Here I can now see all the necessary PROFINET services, including PROFIDrive parameterization. I remove the filter again and take a closer look at the cyclic communication. In our case, a cycle consists of 4 PROFINET frames. 2 for the master output and 2 for the master input. I mark the beginning of a cycle and set a time reference. Now I can measure the distance to the next cycle, which is approximately 1 millisecond with a slight shimmer. I hope you enjoyed the video. Would you like to see more? Then visit our YouTube channel. We will be happy to answer your questions in a personal conversation.